Okay, it's time for autonomous driving. Good afternoon, everyone. My name is Chen. I'm very glad to be here. I'm going to share with you HD live maps for automated driving. And I'm going to focus on how to use artificial intelligence and using all these types of sensor data to create high-definition maps. So first, I'm going to give a brief introduction of our company, just in case you are not familiar with it. And then I will tell you exactly what is high-definition maps. Right, so this is the first time I give the presentation in the Chicago area, and HD map is a fairly new concept. Not many people are aware of it, as well as they are aware of autonomous driving. And in the end, I'll show you using artificial intelligence approach to make HD maps. How many of you have heard about HERE technologies? Okay. What? NAVTech? NAVTech? Okay. So when I joined the company, it was NAVTech. I've been with the company for 12 years, and this is my first job. So our company was based in Chicago when I joined the company. The headquarters in Chicago. At that time, we were NAVTech. It was a startup from Sanibel about 30 years ago or 35 years ago. And then in 2008, we were bought by Nokia. We were with Nokia for a few years. And about 2 years ago, we were acquired by the three German OEMs, BMW, Audi, and Daimler. So we have over 8,000 people. As I'm speaking today, over 200 offices span in 56 countries. So we are a dominant player in in-dash navigation systems. We have 80% of the market share. So if you drive a car that has a in-dashboard GPS navigation system, it's very likely you're just using our map data. So introduction. So here is an open location platform company. It's a global leader of digital map content and location-based content and service provider. So here's a list of our partners we work with on mapping. And many of them are actually our owners. In addition to the three German OEMs, Pioneer from Japan, Bosch, Continental are also our investors. And also Intel actually also bought 15% of us a year ago. And we also work with other partners very closely. All right, so that's an introduction of the company. And next, I'm going to talk about what is HD live maps. Before that, I'm going to give a quick overview of the key components of self-driving. So the first one is sensor. So you have seen in the news, self-driving cars have all different types of sensors. Cameras, radar, LiDAR, of course GPS. Some cars have ultrasound. So all these types of sensors that sense the environment near the vehicles. And the perception. So the software on the vehicle needs to make sense of the data collected. Right? So what is the nearby obstacles? What is the surrounding environment? Where the lane markings are? Is it driving on the lane or is it departing away from the lane? So that is perception. And another piece is the decision, the path planning. Do you accelerate or decelerate? How do you change in the steering directions? And there's another very important component is mapping. So mapping is actually the heart of all these key components of self-driving. So the self-driving car needs to be pinpoint on the high-definition maps to make decisions. And using the sensing and the perception, it matches with the objects, the content in each map for accurate localization. So once the car is localized on the high-definition maps, then it can utilize all the rich information from the map and make intelligent decisions. So that's the background. And in detail, there are 3 layers of maps that consist of high-definition lab maps. The first layer, we call it road model. So this is the layer that everyone is familiar with. Right? So if you come to Glacier Center today, you're probably already using our maps for your turn-by-turn navigation, GPS navigation. So this is the road model. It has a detailed road network, and this road network has many links representing the road, and on each link there are many navigation attributes associated with the link, such as speed limit. Right? If you drive too fast, they give you a warning. So you may wonder where's the warning come from. It's from the map, because we already know what the speed limit is for each road you're driving. So this is the road model. And the next layer is called HD lane model. So at this layer, this is very different from traditional standard definition maps. So at this HD lane model, we have centimeter level accuracy lane boundaries, road boundaries. So this enables safe autonomous driving. So we have the 3D geometry of each lane boundary. Right? So this is in big contrast to the traditional map that you only have a center line of the road, not the lane. So we have centimeter level of geometry of the lane boundaries. We have the we also have the topology of the lanes. We know the association, which lane can turn into which lane at the ramps, at the intersections. We also have accurate road boundary. We have accurate lane type, which lane is drivable, which lane is HOV lane, which is shoulder, that for self-driving cars that can pull over for emergency situations. So that's the HD lane model. And the third layer is also very new. You don't see in traditional maps. The third layer is called HD localization layer. So this layer is for the self-driving cars to position itself on high-definition maps. Right? So it really doesn't matter how accurate your GPS is. You use RTK, differential GPS. It all matters if you can accurately pinpoint your self-driving vehicles on high-definition maps. Which lane your vehicle is at. Longitudinally along the driving direction, where are you at? Then you can use all this rich information of the maps. So this layer, you have localization objects such as traffic signboards, pole-like objects, the barriers. Of course, the lane model also provides lateral localization, that help the vehicle to match what they see on the road to pinpoint it at the lane level. So these are the 3 layers, and these are HD maps. Then why do we need a map, right? So if you're from academia and follow the news, there's a lot of debate. Some researchers, they claim, hey, we just need sensors, right? We just need deep neural net, end-to-end deep neural net, image in, steering wheel, and acceleration decisions out. So then why do we need HD maps? Here, let me just clarify. Of course, road model, everyone knows this is a traditional GPS navigation that provides all the navigation attributes. But the HD lane model, it can provide information that the sensor is really difficult to perceive. Right? So we all know there's limited computing power on the vehicle. And there's limitation of sensors, limitation of computer vision technologies. However, the map can have all types of information. Some information you cannot see from your sensors, you cannot see from cameras, you cannot see from your lasers, but it can be in the map. And also, it's beyond the sensor range. Right? For example, the cameras can see maybe within 200 meters. A good LiDAR scanners can scan within 300 meters. But with high-definition maps, you have all this road lane information infinitely ahead of the vehicle. And of course, high-definition maps provide a precise positioning that you cannot just use road center line map to do that. So in short, why we need HD maps for self-driving? It's very simple. It saves lives. It's a very important safety redundancy layer to self-driving. You can think of this as another sensor, just as important as cameras on the vehicle. Right. So when we provide HD maps, there's a lot of requirements. So first, it has to be precise. As I mentioned, it is a centimeter accuracy level. Has to be cloud-based. All the maps are in the cloud. And so that it can broadcast to the consumer vehicles. And it has to be layered. I already showed you 3 layers: road model, lane model, and localization layers. You can also add, for example, traffic layer. When you get here, you know it takes 30 minutes to get here from suburbs. So that's from the traffic, the ETA estimation. You can add weather layer, right? All different types of layers onto the map. That has to be tiled. For example, if you drive from suburb to downtown Chicago, you don't want to download all the HD maps of Illinois or North America, right? You only download the tiles that can cover the route. And also, last but not least, it has to be fresh. Because the world is changing, so we also need to make our HD maps up to date in near real time. Right? So the freshness is also key. So next, I'm going to talk about how we build this highly accurate and fresh HD maps. So I just want to give you some background. So in NAVTech days, we make traditional navigation maps. So it's already very labor-intensive and tedious job. We have thousands of people sitting in front of the computer screen looking at the video we collected on the road and annotate the maps. So that's just a road center like that. And now we are talking about each lane boundary you have within 10 centimeter level accuracy. Basically, some kind of artist have to manually draw this from our laser scan point cloud data. Right? So you can imagine the amount of work that's involved. So that's why it's very necessary to have artificial intelligence to automate the map creation process. So that's a key. So I'm going to show you a couple of approaches you might have heard of. So first is industrial capture. So big map companies such as Here Technology, they use very accurate sensors. For example, we use LiDAR scanners, not only cameras, LiDAR scanners, rather than LiDAR scanners, to collect the maps and to collect the information all over the world on the road. So it's very accurate. We use differential GPS, use base station to get the positioning information. So that's the advantage. The disadvantage is it's very expensive to collect such maps, or very expensive to even build this type of high-end capture system. So it's not easy to scale. Then in the past probably 2-3 years, we have seen many startups focusing on HD maps using crowdsource-based approach. Right? So you have a fleet of vehicles. For example, if you can get the sensor information from all the taxi cabs, you can actually build HD maps. So the data is very fresh. It comes from the real-time data collection from fleet of vehicles, very easy to scale. And the drawback is the sensor is not that high-end, so it's not that accurate. A lot of noise in the data. Right? So in a perfect world, if it's all the noise is Gaussian distribution, it can be canceled out. Right? So the big idea is once you aggregate large enough amount of cross-source data, the information extracted becomes more and more accurate. Right? So that's the basic idea of cross-source-based mapping. So what we believe is to make HD maps. Right? So we need both. We need to have a very accurate base HD maps from high-end industry capture. That is exactly what Here has been doing. At the same time, once you have high-definition base map, you need the cross-source data to update and maintain the map. We call self-healing maps using cross-source based data. So this is our approach, combining these two. And next, I'm just going to show you each of these two approaches we're doing it here. This is high-end industry capture system. If you live in Chicago area, you probably have seen these vehicles driving on the street a few times. Our office is based in the Boeing building, next to the Metro Ogilvy train station. We have over 1,000 people in Chicago. Right? So we have a garage also based in Chicago. Sometimes you can see these vehicles. So on top, that's our GPS antenna. And that silver metal thing is the Velodyne 32 laser scanners. And under this, you saw 4 high-resolution cameras. Each one is a fisheye lens. And of course, we have inertial measurement unit that can deal with urban canyon scenarios when GPS signal is denied or not reliable. And there's a hardware computer equipment on board to save all the data. Right? So this is the data capture system, and we collect data in North America, West Europe, and some Asian countries. We drive the same roads a few times per period to make our maps fresh. Okay. So next, I'm going to talk about how we automate this process instead of using manual labor to create this high-definition maps. On the left, the video shows you the imagery data we collected, and this is the point cloud laser scan data we also collected. So all the data is geo-referenced, and they are co-registered. So how we extract the lane boundaries, create the lane model layer is that using the 3D point cloud data, we use 3D information, use the reflectivity of the laser points to find this lane boundary and row boundary candidates. And then we make them continuous 3D polygons. That's what you see on the left here. And so then we get the lane information. We figure out what types of lane it is based on the marking types. Is it batch, solid? And then if I superimpose the detected lanes with accurate lane boundary on top of the color image, you can see the lanes are automatically extracted. So on the left, that's an automatic extraction of the lane boundaries of the area in Germany. The paintings are well painted, roads well maintained. So if you move to California, right, so the markings are not well maintained, worn out. It's not very easy to detect from the LiDAR data. So we developed a neural net approach to extract the lane boundaries from perspective imagery. Okay. So the big advantage is that if your training data includes those harsh situations, your classifier, your model can also predict where the lane boundaries are very accurately. Right? So then the next question is, how can you still maintain centimeter level accuracy? If some computer vision people here, 3D structure from motion theory people here, who might question, hey, far away from your camera cannot be centimeter level accuracy. Okay? So our advantage is the LiDAR and the imagery data are co-registered. Once we detect the lane boundaries from the imagery, we back reference to our LiDAR, and we can still achieve centimeter level accuracy. Right. So what you have seen are highway situations. Now, if we move to downtown Chicago, in urban areas, more complicated because of the topology of the lanes, many more intersections, and also occlusions from traffic, from pedestrians. We developed a different approach, but still using deep neural net. We project the LiDAR point cloud top-down, create a top-down view of LiDAR point cloud. So this way, we can overcome the occlusions very well. And we can detect not only the lane and road boundaries, but also classify this and locate the surface markings. So this video shows you use a deep neural net approach. First, classify each pixel. Is it a surface marking? Is it a lane boundary? Is it a road boundary? Is it stop line, zebra crossing? And then we make it continuous 3D objects. So next, I'm going to talk about the next layer of localization layer. Right? So traffic signs are one of the most important attributes in maps, in SD maps or HD maps. In SD maps, that's for navigation attribute. In HD maps, it's more for localization purpose. So the self-driving car can use these signs it detected from the sensor and match with our maps, and then can position itself. So you have seen this red bounding boxes. Those are the traffic signs we automatically extracted from imagery. And with our LiDAR data, we can also find out the 3D shape, geometry, and position of the sign faces for localization. So we can also use a similar approach to detect the poles for localization purpose. And we also developed a very novel approach for localization. This object is very easy to scale. And our customers have proved that using this novel approach, they can sufficiently localize their self-driving vehicles using this data level. So what you see here, this blue cloud is the original raw data from the laser scans, 3D point cloud. Right, so each point has XYZ coordinate with latitude, longitude, and elevation. So the Violin laser scanner can speed out over 1 million points per second. That's very dense, so we can drive at higher speed to collect data. The video. So what we derived is called 3D occupancy grid. We basically, so the red boxes you see is the 3D occupancy grids. So what are they? So they are compact representation of the raw point cloud data. Right? So the customers don't want raw data, it's too big to digest. So they want very compact representation of those objects near the side of the road and above the ground, so that the vehicles can also sense. So these are the 3D occupancy grid. And you can see basically this is a uniformly downsampled 3D point cloud along the edge of the road. To make it even more compact, we use some 3D polylines to represent the baseline of the objects along the side of the road and above the ground surface. Okay. So we go from occupancy grids, these red boxes, to a 3D polylines. And just using these polylines of obstacles, the self-driving cars can also use it to localize itself. And this is more compact. Right. So we have talked so far is high-end industrial capture approach to create HD maps. If you recall, to keep the map fresh is very important. So now next I'm going to talk about how we use cross-source data to maintain and update our HD maps. So we have a fleet of vehicles that can provide us sensor data. Right? This could be from our parent companies, German OEMs, you can provide us the sensor data. Keep in mind, this sensor data is not the raw data, it's not the image they captured, it's not the point cloud they captured. It is the detection from their vehicle. They send us this meta data, the detection data. And we aggregate the data in the cloud, for example, compare with our HD maps, find the changes, and update the changes to verify the maps. Okay. So today, a lot of people talk about machine learning, and even someone showed some self-driving cars slides. So machine learning is important for self-driving, but here I just also want to point out map learning, right? It's another type of machine learning. Is also critical for self-driving cars. So because of the time limit, I'm going to just show you high level how we do this cross-source-based approach to update HD maps. First, you collect this sensor data. Right? This is sensor detection data. Then you aggregate in the cloud, compare our maps, change detection, localization, and then you create new features. Right? If there's a change, or if we have part of the road missing, you have to create new features in the map. then update the map and broadcast back to the consumers. Because this is a feedback loop, right? The original input is from the speed of vehicles, and our updated maps will be broadcast back to the fleet of vehicles to benefit them. So I'm going to skip all these details of each of these 4 steps, but I'm going to show you this is the ADAS function. So if you drive a car that has ADAS function, these are the features they can detect in real time. They will send these detected lane markings, sun bounding boxes to the cloud so that we aggregate. And because it's not just a one single data point, when a fleet of vehicles, when could be thousands, hundreds of vehicles seeing the same thing, driving on the same road, and provide this data. And because of the imperfect GPS positioning, not always aligned on top of each other. And that's a challenging part of using cross-source data to update maps. So we need to aggregate these multiple observations. We need to merge them, fuse them, make it more accurate. So from multiple observations, how do you get more accurate, 7 millimeter level accurate object? That's a key cross-source approach. Of course, then we publish. And, so next, I'm going to briefly talk about how to make it efficient. Right? You probably ask, hey, this is so expensive. The car keep uploading all this data, but it's very expensive to do. 2 approaches. First, we can do some campaign management. You geofence a region that you are only interested in updating, and request those cars to upload their sensor data in this geofence region. That's called campaign management. So the car doesn't constantly collect and upload the data for us. The second approach is that we can move this map aggregation to the vehicle, do this in real time. Right? So the vehicle has our HD maps. While it's collecting the data, we can compare with our maps on the fly and send us only the delta. Right? Not everything, but only the delta that we aggregate the maps. So then, in order to do that, we implemented a reference application for our customers. This is done in real time on the vehicle. And we have a team doing this, so you can see consume 7 watts at video frame rate. We can classify over 10 classes of objects in real time. And this is also, we can detect toll-like objects at very low power consumption at around video frame rate to detect this data in real time, so that we can move this aggregation part in the vehicle. Okay. So this is my last video. So again, in a perfect world, if your GPS is always perfect, then you can use our map information because you can pinpoint yourself just from GPS position. But this is in reality. The red boxes are our maps projected onto the camera in the vehicle. Because of GPS, it's not accurate. You see it's off from what the camera sees in the real world. Right? So then you have to localize your vehicle to correct the GPS errors. So the idea is to match our maps object, those localization objects, with the perception on the vehicle. So once it's matched, then you localize the self-driving vehicles. That is, the orange and red boxes become one unified blue boxes. That means the vehicle is localized on the map. Okay, so that's HD live maps, and we also create a concept or an index called quality index to provide our customers confidence when they use our maps for self-driving, how accurate our maps are. So there's existence. If we say there's a sign there, there's a pole there, how likely there is a pole? Right? I'm sure there's like 5, 6 lines there. And accuracy. If we say this is within 2 centimeters of geospatial accuracy, how accurate that is. And also classification. If the lane marking is yellow, and with deep neural net, machine learning, artificial intelligence becomes more and more intelligent, once these two is combined, the cars become autonomous. So the maps have been used for cars, and also this cross-based approach to make digital maps. You can see maps are also by cars, right? So it's a closed loop. Right. That's why we have been advocating the industry should be willing to share data to make the maps more and more accurate. That saves lives. So it's all about data. Previous presenters actually talk about how important data is. I totally agree. And also how we can enforce best practice in machine learning, artificial intelligence in AI, using this large amount of data. There's a lot to discuss. So I'll be here. If you are interested, feel free to talk to me. And we are based in Chicago. I've been working at this company for 12 years in Chicago. I love the city. If you are interested in working with us on automated driving, feel free to send me an email or talk to me. Thank you. Any questions?
We can take maybe 1 or 2 questions, short questions, please. Thank you.
Would it save you a lot of time if different objects like signs and maybe markings on the road were actually IoT devices that were broadcasting information about themselves, as opposed to your scanners having to assign everything?
Yeah, so the question is, does it save more time if the infrastructure already tells you where the signs are, where the objects are, instead of you detect on the fly? Right? So that's a V2X, vehicle to infrastructure, right, or V2I. My understanding is that it takes a lot of work to do. You need to embed the RFIDs with near-field communication to all the infrastructures. I mean, I just show you 500,000 kilometers of road out there. How soon we can have that? That would be probably the safest. Just we have heard in the media many car companies promising, by 2020 there will be self-driving cars on the market. But can we wait until then? How soon this infrastructure readiness becomes possible? Yeah.
He wants to ask, I can ask you for clarity. Do you want to ask a question?
Yeah.
Go ahead.
You use LiDAR for map creation.
Yeah.
Do you see the need for LiDAR on consumer vehicles? That's fine.
Do I see? So the question is, we use LiDAR for collection, and do I see there's a need for consumer vehicles to have LiDAR? So this is really about the cost issue. So you have seen LiDAR, for example, better than LiDAR, this will cost $80,000 for this 64 lasers. So it's not very possible to have each consumer cars to have such a LiDAR. But you can see the trend is LiDAR becomes less and less expensive and more portable. The size becomes smaller and smaller. So I believe in a few years, each consumer vehicle should have a LiDAR, just like they have multiple cameras on the vehicle. And when the price point drops to a certain point, and so that's my vision. LiDAR will become popular in consumer vehicles in a few years. Okay, thank you.
Thank you, Dr.